Sir, I'm unable to hear. Please unmute your mic, sir.
Okay, sure. Okay. I would like to start with introducing myself to everyone. My name is Amr Abdel Fattah, and I am also known as Amr Muslim from LinkedIn. And I have already 16 years of experience working in oil and gas industry. I started with a service company, and then I joined E&P company in 2008. And since then, I'm working as a senior staff geophysicist. Also, recently, I already start the journey of machine learning and coding since 2014. This was my passion only, and then start to evolve from just a passion into a profession with the current company I'm working with. And that's was my lucky motives. This already I met the machine learning evolution in 2014, and I started since then to learn machine learning bit by bit. And then I did some interesting applications in geoscience, and we could do a very good job in using machine learning for geoscience and for exploration and development. I will share with you some of these applications already. But first, we will go through a short introduction for the machine learning algorithms and machine learning classifications, and this is how this all works. So we will try to make it bit pieces so we can digest them, and then I will show you some of the interesting applications in geoscience world, and from there I think you will see the value of machine learning in geoscience especially. And at the end of the day, I will give you a roadmap for starting learning machine learning. What should you do if you want to do to go this road? What should skill set you should acquire during learning in this journey. I will start. This already the agenda I have, and then I will start already with a simple definition of machine learning. Can everyone hear me quite okay? I get comment from a friend that we already have issues. Can everybody hear my voice? Okay.
Sir, we can hear your voice.
Okay, perfect. Great. So I will start with the simple definition of machine learning. Machine learning is a new field of artificial intelligence that allows systems to learn from past data and make intelligent decisions. And I want to make, I want to grab your attention to the highlight colors words here. So this are the keywords already in each slide. So it's part of the artificial intelligence that allows systems, the computers, to learn from past data and make intelligent decisions on their own without doing any without any explicitly programmed, and we'll know this in a bit. I don't have to do if you find the value is above certain threshold, so you can do this operation, or if you find the value below this cutoff, you have to do this equation. Though we wanted the system to learn from the data itself, to find the relationship between the data itself together, and then improve its experience. What does it mean, improve its experience? It means the algorithm will start with some bunch of assumptions, and afterwards it improves the experience of prediction and the experience of making intelligent decisions. This is what we wanted the algorithm to do, keep improving its predictability all the time. This slide you will see. Sorry. Okay. You will see what's the difference between machine learning and common coding. In common coding, I will highlight here in this part of the table is the example. This is will give us a good insight, and then we will move through the other parts. In machine learning, you have data which could be mass, height, width, and velocity, and this the same data we have already in common coding. But in order to calculate the velocity, what we need is to know the equation. The velocity equal distance over time. So we need to have the equation first. After we have the equation, we make a function that calculates this equation and return the velocity as we need it. But in machine learning, it's totally different. The machine learning, we can have different types of data that already directly related to the velocity, but not necessarily related to the equation of calculating the velocity. And then we already perform one of machine learning algorithms. We'll have a bunch of them, and we will discuss any part of them. And then I will make this model do a fitting problem, fitting process or fitting step, which is the step the algorithm learns from this data. And then we'll have the final step, which is the prediction, which is already predicting new data after I have already after the algorithm already learned from the past data I have given to them. So this is the block or the steps of the block in machine learning, which is already calculating the velocity. Here we have a direct equation. I have to write the equation as it is, as a physical equation. Here, as you can see, we don't have anything really related or directly related by an equation for the velocity, but we can generate some relationships between the data itself by knowing the values of the velocity. So the algorithm is learning from the past data, and then the algorithm will find the relationship between these parameters and the velocity data, and then it will already perform the learning process, its learning process. Let's go for the other inputs in the table. As you see, the objective of the machine learning is to teach the machine to create models that solve problems without hard coding. This is what we call it hard coding. Hard coding is to do the physical equation in coding. This is hard coding. So without hard coding, using just the data patterns, so the algorithm will go inside the data and see how the velocity reacts when mass changes, how the velocity reacts when the height or the width of the object changes. So this is the pattern that the model trying to find in the data itself. The common coding is to use programming language to explicitly code, as we mentioned here. This is hard coding the problem. So if I don't know the physical formula, the physical equation, I cannot do any prediction with common coding. But with machine learning, if I don't have the exact formula, I can still predict the behavior of the velocity. The tools we can see here, we have a bunch of tools for every one of them. In common coding, we have all the programming languages. plus Excel as well. In machine learning, we have Python or scikit-learn, which is a library for perform machine learning models. We have TensorFlow, which is another library from Google that already perform some certain models and equations and the steps for only machine learning models and deep learning, of course. The running time in machine learning, most of the running time is already in data wrangling and the model evaluation. However, we will see the whole workflow right now, but 80% of the time you are just working in data wrangling to make the data in a proper format that the algorithm can run without any problems. In common coding, we have most of the time in coding the problem and doing the equations, doing our model, the equation itself. The output from the machine learning will be the model and the forecast. The output from coding will be data tables, graph, dashboards, and so forth. Reproducibility, both of them can be reproducible. Domain knowledge, which is very good, very important one. In machine learning, domain knowledge is very important and highly recommended, but it's not a must. Which means I can know about the subject, but I'm not. It's not necessarily to be an expert in this subject. But in common coding, you have to be an expert because you have to know all the equations and all the assumptions and all the conditions of every equation you have. So in machine learning, you can solve the problems. You are not really a very experienced one, but you have to have a very good knowledge deep inside this topic, so you can know how the machine learning model is performing. Is it okay? Is it good? Is it bad? We need another algorithm. This can be of a good prediction or a bad prediction. So this is already this is all in domain knowledge. So you have to have a very good command or knowledge about the topic you are doing. Okay. The next slide is we are talking about the machine learning classes. I bet you already heard about this before, but machine learning has two big classes, which is supervised machine learning and unsupervised machine learning. And these are two different animals, two different things. The first one is supervised machine learning, where you have the data and you have the answer as well. You have the label data. So we have the data and we have the answer, and we are trying to make the algorithm find the pattern and the relationship between the answer and the data itself, like the velocity example we already talked about. If we find the relationship between or the pattern between the data and the answer or the label data, this will be you're solving or the problem, and you can predict otherwise. So in supervised machine learning, you have to have the answer as well in order to allow algorithm to learn from the past data and then make the relationship or find the relationship between the data itself. Or reference or the answer, as we mentioned, model should be continuously tested based on the label prediction or classification. In unsupervised machine learning, it's a different animal, as we talked before. The unsupervised machine learning has no labels, which means that I have data and I don't have the answer. So what else I can do if I don't have the answer? What prediction I'm expecting to? The prediction here is to cluster the data, to reduce the number of dimensions in the data, to make some preconditioning and some formation of the data in order to make it easier to be understandable. So in unsupervised machine learning, the data has no labels, no reference, no answer, and the data learn from itself, not from the labels. The model should be judged, not tested, and we will talk about this in a bit. Judged, which means you can say this is good for me, or no, I want to more clustering, for example. So this is already your own criteria. So basically we have two types: supervised machine learning, where the data, I have the data itself and the label data, and unsupervised machine learning, where I have only the data without any labels for this data. Okay. The machine learning algorithm, we have a bunch of machine learning algorithms, a lot of them, and I'm listing here just the most common ones, the famous ones, starting from linear regression, logistic regression, decision trees, support vector machine, naive Bayes, k-nearest neighbors, k-means, random forest, dimensionality reduction, which is PCA, gradient boosting and its family, gradient boosting, XG gradient boosting or extreme gradient boosting, light gradient boosting, and the cat boosting. This all fancy names are based actually on mathematical and scientific approaches and the statistical approaches as well. But everyone is very good in type of data. Is there any have any questions? Hello? There any questions?
No questions, but I think you are going to give the use of every type of this algorithm, right?
Every algorithm has its own pros and cons and has its own strengths as well. So some problems we can use linear regression, but in other problems we cannot use linear regression.
Okay.
Sure. Okay, and in the right-hand side, we have here a classification graph that already listing most of these algorithms inside the categories we were talking about, the supervised learning or unsupervised learning. And we can see here a simple definition: data with label, data without label. Reinforcement learning is different thing, and we will have another session for it if you would like. This is a booming branch of machine learning, but it's not for the scope of this session. But we have here, as we mentioned, data with label and data without label, and we can see here categories: classification, regression, clustering, and association problems, or dimensionality reduction. And we will see how this is going to work with us in the coming slides. But the main objective from this slide is to tell you that we have already a lot of machine learning algorithms. We can use all of them, and we can we cannot use all of them, and these are the most famous one. The one, if you already know them, you have like 80% of whole problems you are going to solve with machine learning can be solved with this simple algorithms on the left hand side. So I can assure you, if you just learn these 10 or 13 machine learning algorithms, you will be past the intermediate level, and now you can handle any problem you face in your work with these just algorithms. Can you excuse me for a second? I just need to connect the charger and come back to you.
Okay, sir, it's okay.
I'm sorry for the inconvenience, but it's better now than we should do it later. Okay, here's we are going to talk about the types of each algorithm. We have, as we mentioned before, we have two big classes, two big categories or classification for the machine learning: the supervised machine learning and unsupervised machine learning. Here we are going to talk about the job of each one of them. In supervised machine learning, we can do regression and we can do classification. In unsupervised machine learning, we can do dimensionality reduction, and we will talk about this in a minute if you don't know what is dimensionality reduction. And another thing, which is clustering. Why here we do regression and the classification, and why here we do different jobs like dimensionality reduction and the clustering? And this is all because the label data. If I have a label data, which means the answer for my question or for my problem, so I can do prediction based on the pattern between data and the label data. So I can do regression and I can do classification. But here I have just the data without any answer or without any labeled data, without any purpose to make prediction. So in this case, what I can do with data is just a clustering to cluster the data to make it separates, or I can do dimensionality reduction, which means if I have like 10 dimensions in the data, 10 columns, I can reduce them into 3 or 4 columns with confidence without losing any information. This is the tricky part, without losing any information or without losing the most of the information. And I will talk to you about this one in the coming slides. Firstly, let's see the definitions of regressions and every one of them, and then we will see in the application how we can use them. In the regression is what we used to do in the college, what we used to do in high school is just to find the best fit line between the data that describes the relationship between 2 or more parameters. But in machine learning, we don't have only two parameters. We have more parameters. We have like 10 parameters. We have big data, so we have a lot of things to do to find the best fit between them. So a regression is a set of a statistical process for estimating the relationship between dependent variable and independent variable. And we have a lot of algorithms for regression, like linear regression, logistic regression, polynomial regressions, and a lot of things. And in regression, the data should be always numerical values, not categorical values. So we cannot make a regression based on categorical values. Categorical values is just the text, for example. Like if I have facies log and I have already sand, shale, limestone, whatever it is, so I cannot make regression for categorical data or text data, but I can do regression for numerical data. And one of the examples we already use heavily in geoscience is missing logs prediction. Missing logs prediction is a very common, I can say it's a day-to-day task. If you are working with an E&B company, most of the times they wanted to save money, so they want just to run the logs based on their server section only. Nobody cares about what's above and what's beneath. But if we wanted to extend your study later on for different formations or different reservoirs, or you wanted to study the ceiling, the source rock, you wanted to extrapolate your logs. And extrapolating logs is not a very good job unless you are doing it with machine learning. I think will be much better. Also, most of the old data, we don't have shear sonic logs, which is very essential when we are doing EVO analysis, for example, or inversion. So it's a very good approach. And I think it's become normal now to do shear log prediction using machine learning. Next, we have in the supervised machine learning category as well, we have classification. And the classification is another word for categorization. And as suggested here in the image on the right-hand side, that we had draw a line between two different categories, two different classes. So it's basically to rearrange the data you have according to a criteria with
Not visible, not audible.
Что, тоже домой пойдем?
Опять дома в магазин поиграем.
Дома, да? Ибрагим с мамой. What's happened to the class? It's interrupted. It's interrupted by the...
Hello, everyone. Just wait for another 5 minutes. Sir is joining again.
Yes, sir.
Thank you.
Sir.
I'm sorry for any inconvenience. I don't know what's happened, but I changed my hotspot into another one, and I hope it will work till the end of the session. I will coming back to supervised machine learning. We have the second category, which is classification. And in classification, as we mentioned before, we need to classify the data based on a predefined classes. So I have the bunch of data in all wireline logs, and I want to classify this data based on the fishes log I have into sand fishes and shale fishes or marley fishes or limestone fishes. So in order to make classification based on the data, like we do actually in by ourselves, I went to the machine to do it. So I have to have predefined the classes first, and then based on the pattern and the criteria of every log, I should change or I should put this data into a shale class or sand class. And the example of this, the very famous example of fish's problem is fraud detection. How our inboxes know that the coming email is a spam or not a spam. And in geoscience world, we use fish's classification as one of the supervised machine learning widely used in the industry. The second, we are going to talk about the unsupervised machine learning, unlabeled data type of machine learning, which is the unsupervised machine learning. And we have two subcategories, dimensionality reduction and the clustering. And I will going to define what is clustering first, and then we will go to talk about dimensionality reduction. Clustering is pretty much like classification. It's very close to each other. However, in clustering, I have no predefined classes. I just want to separate the data based on the data itself without any labels I have, without any faces. I just wanted to put the things that looks like each other together. In order after this, I can do a different tasks like predictions afterwards. But firstly, I wanted to make it subgroups. So this is the clustering, to do a classification without predefined classes, and we already do this in geoscience world, which is the most famous application for it is also fishes classification, as mentioned here, but fishes classification based for the first time. If I don't have facial log before and I want to create a very fast facial log, I can do clustering. And after I finalize the clustering, I can afterwards refer to these classes as sand or whatever. So the very first time to do facial log, I can use unsupervised machine learning clustering, and then afterwards, after creating the first one, I can use it as an input for supervised machine learning classification. So most of the time you will find you're using unsupervised machine learning as a preconditioning or a conditioning for the data for the supervised machine learning classification. Another example in different industry, which is customer segmentation. In customer segmentation, we wanted to cluster or separate our clients into different groups, so I can treat them based on their segment, based on their power of purchasing, based on their behavior, to make their experience is a better experience in my shop or in my marketing plan. So I need to do a clustering for these customers, and I don't have an ideal customer, or I don't have a profile for the customers. So I just wanted the machine learning to classify them based on the age and the purchasing power, maybe their marketing plan, the area, whatever it is. So in customer segmentation, we use already supervised machine learning. And this has been in industry since, I think, 10 years so far. So customer segmentation is one of the big example for unsupervised machine learning clustering process. And in geoscience world, we have already facial classification for the first time. We do it as unsupervised machine learning clustering process. And the final one here in the categorization is dimensionality reduction. And dimensionality reduction, this is a big problem actually. Imagine in our world right now, how many data we have, how many data can we acquire. Imagine your Facebook profile and how labels or how columns do you have in your Facebook profile. I would say like we have hundreds of dimensions for each Facebook profile, starting from the day you born, the month you born, where the location, your interest in science, your interest in sport, your interest in education, how many friends you have, what education you have. A lot of data you have, and this data, every column of every category I mentioned is already a dimension. So if you have 100 dimensions for one profile, imagine for 1 billion profile, you can generate a lot of dimensions. And these dimensions, when we already running machine learning algorithms, it's so powerful. It needs a lot of computation time. And sometimes some data is already redundant. Some columns or some features are already redundant. You have it already in other thing. Think about it. If you are trying to look for an apartment and you have the length and the width of the apartment, and also you have the area. So the area is already multiplication of the width and length. So instead of have 3 features, you can have 1 feature only, which is the area, that already describing the length and the width as well. So the length and width of the apartment will make a redundant data for the area as well. So in order to have an efficient computation, you need to remove the redundant data. This is the first thing. And second thing, in order to make it fast algorithm, to make sure that you already get a fast and effective algorithm, so you can do a lot of trials and make it dynamic, you need to have a limited number of dimensions this algorithm should work with. So the dimensionality reduction here is the algorithm that already look into the data and try to find the most interesting features or convert the data into different dimensions where most of the information are preserved in a number of dimensions. And this is the tricky part, as I mentioned before. Most of the informations, the variances, are already concentrating in a limited number.
Sir, you are not audible.
Not audible.
We can't hear you, Abu.
I'm sorry again, everyone, for the inconvenience, but I think I have some sort of problem in the internet connection. Sorry for this, and bear with me. I changed my hotspot again. Okay. So the main objective of the dimensionality reduction is to improve computational efficiency without sacrificing much prediction capabilities. Also removes the collinearity, as I mentioned before, the example of the flat, and you have already area and length and width. So if you remove the length and width and keep the area, you are removing the collinearity as well. So you remove the redundancy and you make your prediction more efficient. Okay. In this slide, as you can see, we have different dimensions we are working with. We are the geoscientists. We have different dimensions we are working with, starting from the one dimension, as the gamma ray here suggests. Then we have 2D maps, which is a 2D representation, and we have 3D cubes, which is a 3D representation. Adding seismic attributes, for example, like 3, 4, 5, 6 attributes. This is adding dimensions. This is adding more data, but also adding more redundancy to the data, if you can say. And Richard Bellman, one of the biggest statisticians, has this concept of the curse of dimensionality. And it says, if the more you have data, the more effort you have already to make this data all fit together. And we are also humans. We cannot actually visualize more than 3D. So it's have more dimensions, give us any limitations, give us limitations in visualizing these data. So in order to better visualize the data, we need to make it into 1D or 2D or 3D dimensions. Okay. I would like to have like 5 minutes before we continue here for questions. If anyone has any question regarding the topic so far, and then we can continue from here. Thank you very much. If anyone has any questions so far? Okay, I will keep going, and if you have any question, please write it down in the chat, and I will open it again in order if there is any questions I can answer them while we already have our sessions. Thank you very much. Okay. Now we are going to see how we are going to work with machine learning. What is the workflow that should machine learning do it? So it's a basic workflow, but it's very important, and it's already all the problems you are going to work with, it will follow this workflow. Starting from input data. So we have data, we have to input data first, and then we will start with something very, very, very important, data exploration. And this concept has been introduced by in 1947. The one who is introduced it is Dr. John Bayer, I think, and this one is very important because it has already a published paper in 1947. It was talking about the importance of data analysis at that time, and he draws the attention of the whole world to that we are going to have more value of the data and the information that it was at that time, and this has come very true by the era we are living in. So data exploration is the first thing you have to do after importing your data. Data exploration is to understand the data, to understand the limits, to understand if you have collinearity, which means 2 or 3 inputs or more inputs have the same pattern. If one increases, the other increases, or have a reverse pattern. If one increases, the other decreases, or have sort of any relationship of any way. This is data exploration. Then you will start with cleaning and filtering and fixing the data. And this is what we call it data wrangling. Both of them are data wrangling, starting from data exploration and data cleaning. Both of them together are data wrangling. So you have to have data wrangling in order to make your algorithm run smoothly without any problems, but not only problems, to make it work efficiently as well. Because some algorithms need the data to be on the same range, like you have to do standardization or normalization as we do in well logs. Some of the algorithms, this is a requirement. You have to do it. Some algorithms, they like linear regression, they don't work with categorical data like strings or text, but you need these categorical data as one of the inputs you have. It's a very important input. In this case, you have to transfer the categorical data, the text and strings, into numerical data. And this is part of the cleaning and filtering and fixing. This is part of data wrangling. It's very important. I cannot stress enough. And if you leave time for me to talk about data wrangling, I will take all day. So it's very important, and 80% of our time in machine learning, or as a machine learning engineers, we do data wrangling first. Then we change the data a little bit, as we mentioned: data conditioning, standardization, normalization, removing redundancy if we see it, removing collinearity if we see it, handling missing data, because some algorithms cannot handle missing data, or 90% of the algorithms cannot handle missing data. So in order to decide which values are going to fill in the missing data, or are you going to remove them completely, this all said is different feature engineering. Features is the columns, and engineering is to redesign, re-engineer these features. Not only feature engineering, including just filtering or changing the shape of the nature of the data, but also data selection, because not all the data, as we mentioned before, as useful as each other, or have the same amount of predictability as the others. So you have to select carefully as well the amount of data that you are going to use in order to make your machine learning model efficient and fast as well. Then afterwards, we do a train test split. Train test split is because we want to judge the algorithm. We wanted to know if the algorithm did a good job or not. We need to divide data into training data, that the algorithm will work on it, and test data, which means the algorithm, the part of the data that the algorithm will be tested based on upon this data. So part of the data will go to training, and another part of the data go to testing. And by testing, this is where you change the model, define the model, change the hyperparameter of the selected model or the selected algorithm. And then based on this one, you select already the model and you do evaluation after training and testing here in this process and performing the machine learning process itself. And then you do evaluation. And after you do evaluation, you can go back to cleaning or filtering. You want to remove some of the data, you want to add some data, you want to change the shape of the data, and you can go back to feature engineering, or you can go back to feature data selection and filtering and so forth. So this is the workflow of the machine learning. You start with input data, data exploration, doing some filtering, cleaning, missing values, handling. Then you train and test, split the data into train and test, and then you select your machine learning model and do machine learning evaluation, model evaluation to see if the model is performing good or bad, or you can be the model can be improved, or this is the best you can get. And then if you want to go back to any of the before steps, you can go back, of course. So this is basically the machine learning workflow. Okay. In this slide, we are going to discuss the train test split concept. Usually, if you wanted to split your data, you split your data by two partitions. One is training and the other one is test, as we see here, training and testing. Training usually takes 60 to 80% of the data, testing taking the rest. But there is another concept as well we wanted to introduce, which is the validation. So instead of just splitting data into training and testing, you split data into training, testing, and validation data set. Why this? Because we want to make sure that the machine learning algorithm captures everything in the data. And we wanted to make sure that the machine learning algorithm can work blindly on different data sets. So we took the testing data or the validation data aside from the data itself and work to put it aside completely, do our machine learning selection, hyperparameter testing, and everything. And at the end of the day, after we finish everything, we test for the last time our machine learning algorithm on the validation data set. So if we see it works good on the validation data set, that's the data that has never been seen by the algorithm, which means the algorithm is doing a very good job. If not, it means we have some sort of improvement we need to do to the algorithm. So we can return back to the model and change the model. We can change the algorithm, we can change the hyperparameter of the algorithm, the parameterization of each algorithm. And by doing this, we already improving the model and making our model doing a better job. Each time you can select to have a fixed training data set and testing data set and validation data set, they are fixed rows, fixed amount of data, or you can choose to make every time or every iteration they are different. For the first example, as you can see here, the blue color here is the training, the top part of the data. Here the middle part, and here the bottom part, and you can change, as we can see here, between the data rows all together, in order to make sure the data is already has been seen for training and for testing and for validation as well. This will be your choice. Nobody will tell you what to do, but the best way is to split the data into 3 categories: training data, testing data, and validation data. Okay. Now we are going to talk about what after I'm doing. I did already the data cleaning and filtering. I did the feature engineering, the model selection, and data split and validation split. And now I want to evaluate the model. How can I know that my model is doing a good job or not? This is the model evaluation. Okay. The first thing we'll start to make to be able to do model evaluation, we need to choose our loss functions. In regression, it's very simple. We have these loss functions. It's mean square error, root mean square error, and R squared. And we already know all of them, and we are exposed to all of them. So in regression, it's very easy to choose one of them, and it's already built in functions in most of the languages and also in Excel. So we are pretty sure of the loss function or the cost function, as we mentioned in some of the literature. But this is the most important one: how to do the model evaluation. As you can see here, we have a graph here with error rate and the model complexity. Model complexity means 2 things here: the timing of the model running, which is the iterations, and another thing is the model complexity, the change of the model parameter. So if we change the model parameters, and if we give more time to the model to run, the more iterations, as you see, the error rate is decreasing all the time until we get stabilized rate. And this is the rate of stabilization for the model. This is what is the best the model can do. Okay, this is the error rate, and this is the number of iterations or model complexity. This is for the training data. This is not only for the evaluation, not for the testing data or validation data. This is for training data only. This line. After you did some tests on the model evaluation, you find a very interesting feature. The error rate for the testing score or testing data is going down, and after certain amount, it's going up again. This is a very interesting criteria, actually. Here in the training data, we keep lowering the error rate all the time, until you maybe find that you have 0 error rate, which is 100% score. But for the testing data, you see that you already have lowering the score, the error rate, the error score, and then you start building up again the error rate, which is very interesting criteria, as we mentioned. But why is this happening? Here, the model is still early. It's trying to understand the data, but it's still early. We need more time to understand the data. Exactly as we already tried to learn a new language or new science. If you spend like 2-3 hours, it's still too early. You need to spend at least 20 hours to be to understand the subject, and you need to spend 10,000 hours to be an expert in subject. But afterwards, after a little while, the algorithm, he keeps data, he memorizing everything, he knows the data by heart. So in this case, the training error is low, but the testing error is high because he knows your data very efficiently. But he knows data not because he already understands the patterns, but because he already knows the values. He knows he make a model for every single value, which is very bad. Okay, I will discuss this afterwards, but let's see this first. So the first part of the graph here, we call it underfitting, where the data here, the model is assuming a very simple model for the data. As you can see, the data here should be treated as bi-model, 2 direction or 2 orientations, and he treated the data as a linear regression with 1 model. So here, the data is underfitting, or the model is underfitting the data. On the other hand, of the other side, the model here treating every point as if it's already a model itself by its own. So he creates a very low training rate. But if you add a new data points here or there, it will give you a very high testing error rate, which is not very good, because you already know that you have a very good error rate, but actually you have a very bad error rate, and this could be quite tricky, and this is why we do model evaluation. What we wanted to do is we wanted to have a good fit, which is a more generalized model fitting the whole point of the data. As you can see here, now the model knows that we have by model data point, not a linear one or not more squiggle as we see here. So this is a happy medium as we see it, and this is the most important step. And that's why you have to create this graph every time you're changing parameter, and to see where we should stop the model, where we should stop the hyperparameter, as we already doing our model complexity. Okay. The BAST graph was for the regression problems, but for classification problems, we have different thing. We have classification, for classification problems, we have confusion matrix. Confusion matrix here, where we have the predicted classes and the actual classes, and we have 4 categories for each class. Either it could be a true positive for true positive data, or true negative for true negative data, and we have two falses, false positive and false negative. And as we already know in this pandemic, if you wanted to go to do a PCR, or you ask for accuracy of the PCR, you will find in the literature a lot of things talking about the confusion matrix, because it's already developed from there. So if you already a sick person and you already have corona, for example, and you did the test, and the test tell you that you're already positive and you're already sick, so it's true positive. And if you already a healthy person and without any sickness, and you did the test and test tell you that you're already negative, so, and you already a healthy person, so it's true negative. But in either ways, if if you are a healthy person and the test tell that you already positive, so this is a false positive. And if you are a sick person, or you already caught coronavirus and you already tested negatively, this is a false negative. And this is how the confusion matrix works. And this is works only for the classification problems, as we mentioned before. And from this 4 boxes, we derived a lot of criteria here: the precision, the recall, the accuracy of the whole thing, and the F1 score, which is already representing all these parameters. I'm not going to dig deep into confusion matrix, but if you want to, we can talk about it, and I think we will talk about it in classification problems later on. Okay. Here I will try to speed up a little bit, but here we will see how the machine learning works. Now we know the algorithms, we know the model evaluation, the workflow, the classification of the algorithms, what machine learning can do, what cannot. Let us see how it works actually behind the hood, without telling us how it works. We will see from behind the curtains how the machine learning works. I choose to do this experiment with linear regression because it's very easy for us and very intuitive, and we have done it in high school and in college like 100 times. So it's very easy for us to understand it without any other complications. So the objective of the machine of the linear regression, the normal linear regression, is to find the best fit line. And this best fit line is following this equation: y equal ax plus b, where a is the slope or the gradient and b is the intercept or the anchoring point here on the y-axis. So this is basically how we do already the linear regression, and the objective is to find a and b in order to know what is the best fit for this data. If you go back by your memory and try to remember how we do this in college or in high school, we basically assume a bunch of numbers with fixed increment. Like I will start with 1, 2, 3, 4, 5, 6 with fixed increment, and I'll choose A, for example, as 1. I'll choose second time as 2, 3, 4, and calculate the predicted y, and see y predicted minus y actual, and see which value will give me less error. As you can see here, we choose here A like 1, 2, 3, 4, and we try to see the y predicted minus y actual, and we see what is the error value. And as we approaching to the correct value, we see already the error going down till we get the correct correct value, and afterwards the error is getting up again. So we know that we already going far from the correct values for A, for example. And here we choose the A with the lowest error value, and that's it. This is how we already do linear regression in the past. How machine learning is doing linear regressions? This is very important. And if machine learning is a human being, it will have two legs. First one is generalization. Second one is optimization. What does it mean, generalization? Generalization is what it's here actually. Here the model is generalizing, because if it doesn't generalize, it will be underfitting or overfitting, as we can see here. So we need the model to be generalized, as we can see here in the good fit situation. And the other thing is optimization, which means what does it mean, optimization? Optimization is you start with random value, anything, and then you start to get better and better in prediction every time, getting better and better in prediction until you find the better value or the best value. And how we do this, we are looking into this graph. So the error function, as we can see here marked in red color, this is the error function. This is the true minus, the predicted minus true value squared, in order to see how its behavior, how it works. So this is the error value, and as you can see here, the error value is acting as x square formula or x square behavior. And what if this is the solution here? What if we could find the value here? What takes us to find the value here? If we get the tangent here is the first slope from the derivatives. First slope. The first slope is give us the slope, or the first derivative, sorry, give us the slope of the error function. And here in the bottom, where we have the optimum value or the best value for the slope, we have a tangent of a horizontal line. A horizontal line has a slope equal 0. So if we get the slope of this each point at this function, and we make it equal 0, this will be the correct value. This will be the value we are looking for. So it's very easy. We just wanted to derive the first derivative of the residual function, or the cost function, or the loss function, or the error function. All are these synonyms. So if we want to get the first derivative and make it equal to 0, and find the x value in this equation, this is what will drive us into the correct value. Exactly at this point. So the first thing is just get the first derivative and make it equal to 0. First derivative of the cost function. The second thing is how we are going to move. As you remember, in the past, we are moving by fixed increment. And this is not a very good approach, because you can try thousands of values. You can try millions of values, and you didn't get to the correct one. It's depend on which increment you are using. And if you use a very high increment, like every 10 values or every 100 values, you can quite easily miss the correct value. So in machine learning, how we do already this without losing the correct value, we are doing it by what we call it learning rate. The learning rate is not a fixed value. it's a fixed percentage of the error, which means if I have a big error, I will take 10% of this error and move to the next step. So if my first guess or random value was here, and I will take 10% of it, it will be here. The next 10% of this value will be smaller than this big jump. It will be here. The next 10% will be here and here, and will keep diminishing because it's a percentage. It's not fixed value, it's a percentage. So it will keep closing and close till the correct value. I have already a GIF file. Next slide. So pay attention. It's describing the whole situation I described already, but in visualizations, so you can see it better. As you can see here, this is the error function I have told you about, and this is the best fit line. And as you can see, it starts with random value and calculating the slope and making the slope equal to 0. And then we change the learning rate by steps. And as you can see, the first jump is big one. Second one is less and less and less until you get to the correct value. This process is called gradient descent. Gradient because it's going into gradient steps, gradual steps, and descent because you are going from high error into lower error till you get the best value of the prediction you can get. As you can see here, the first jump for this line, the best fit line, was big one because the error is big drop, and then it keeps optimizing the value until it finds its best value. And this is how graded descent working automatically without any human interference. So this is all. You are not going to see this. You are not going to do this in Python or in R or in any other language. The machine is doing this behind the curtains. I'm just telling you how it works under the hood, so you know how it works and you understand that machine learning is not sort of magic. It's based on a mathematical and statistical procedure. Gradient descent has some characteristics. It's based on calculus, as we already mentioned earlier. It's the first derivative or the other derivatives for complex problems. Gradient descent is different from algorithm to another. This is we have to be careful of this one. Gradient descent for complex problems, especially for neural networks and deep learning networks, has local minima, like this one, This is the global minima. There is local minima, and this is local minimum as well. Learning rate is a very essential step, because if you choose a big value for learning rate, you could easily miss the correct value, and this will lead to inefficient calculation and inefficient prediction. Learning rate can be caused of overfitting and underfitting as well. So you have to be careful how you choose the learning rate. And this is a parameter this is one of the hyperparameter in the machine learning models. Okay, we are approaching to the end of our session. So if you have any questions so far, I will be happy to answer them before we get into this one. Nice. I think we have a lot of questions. Thank you very much. Thank you very much. Is there a negative trade-off? Is there a negative trade-off? What do you mean by negative trade-off? Varying number of ways of reducing dimensionality. How do we choose the right one? We don't choose, the algorithm choose for us, and it's not choosing, by the way. The algorithm is changing the data into a new data set that has already most of the variance of the data, or most of the information in the data. So we are not choosing, or we are not selecting some columns. The algorithm, it changes the whole data set into a new data set that already containing most of the information in the data. In training and testing the data, how can I prevent the overfitting problems? This is a very good one. In training and testing, first of thing, you have to be careful when you choose the percentage of training and testing. And this is also based on the problem definition. If you are talking about, if your problem is something like time related, the production forecast, for example, you have to choose the last period as your testing set. But if you are doing with continuous data like porosity, for example, permeability, something like this, or shear wave, it doesn't matter if you have certain portion of the data. You have to have your test data random. You have to choose the testing data random from the data itself. So you make sure that everything is already and every feature or every pattern in the data is already captured, part of it in the testing data and part of it in the training data as well. In splitting data into 2 or more datasets, would this improve the model performance if the input feature have a different trend with the data? This is the same question and we answered the same way. Yes, you have to choose your testing and the training data, capturing all the trends on data. Sometimes the data we have is imbalanced data, which means we have some certain of features that what is not already well distributed over the data. Like if we have dikes, for example, in fishes classification, these dikes are very localized, not in all the section, and it's not surround in the whole field. So I have to select the data to include already the dikes with a balanced degree. And there is already some predefined solutions for imbalanced data as well. Does our coefficient can inform us about validation of the model? We use it R squared. You mean R squared is a controversial one, but we use it already in order to make to know that we already have a good prediction over the model, but we have to be careful, of course, because it's describing the whole data set in one number, and I agree with you. We have to be careful when we're choosing this. That's why one of the model evaluation techniques is to plot the data again, to visualize data again, to visualize the input and the output data, the data label and the predicted data as well, the actual and prediction, and to see if it already similar or have a good prediction or not. Because statistically, R square can be high, but actually can be wrong. And this is already a well-known problem. Very good question, Glory. For unsupervised learning, fishes classification may be called fishes clustering, since it's groups fishes based on similarity. Yes, absolutely right. But since the common name is fishes classification, we use it here carefully, because the word classification means different thing in machine learning. Yes, you're right, Glory. What about form of certificate? I will leave the gentleman in Edvantage to tell us about the certificate later on. Let's complete the class, please. It's not time to ask Omesh. Okay. Sorry for disturbing you, Meshi. Is it possible to recommend any links where we can access sample problems to practice machine learning. Absolutely, I will do this. I will at the end of the session, I will give you the link of my GitHub. It has a lot of problems and has a lot of solutions as well. You can get good knowledge out of my GitHub, and it's all, I think, public, so you can go and dig deep to whatever you like. And by the way, this presentation is already in GitHub, so I will give you the link as well. And I will give it to the gentlemen in EDvantageindia, and they will tell us, share it with you, of course. Please, I need to ask the amount of data that is adequate for perform machine learning prediction. There is no amount of data to be specific, but rule of thumb, they said if you have less than 50 data points, you cannot perform a machine learning algorithm. But I have another solution for this one, but it's a little bit advanced. But we can do this anyway, because we have core data, and core data is always limited, and we want to do machine learning on core data. And I know that core data is very limited, so we have to find a solution for it, and we already did. I have few data available from past work, so yes. Please, and you can contact me, and I will tell you how this. But I think it's out of scope for the session. But you can search, of course, for different one. And I'm planning to have a paper in the next SPE. This paper will discuss how we do machine learning prediction for core data. And as I mentioned, it's very few data points, but we can do this one. What ratio should be used in training and testing? Usually training data is from 60 to 80 and testing from 40 to 20. And you can split the testing data again into half of them into testing and half for validation, as we mentioned already. Thank you very much. Okay, thank you all. I will have like, I think 10 minutes, and then we will be finalizing. Thank you very much. Okay, so let's dig deep into the machine learning application in geoscience. And we have a very good and interesting applications I would like to share with you. And if you have any other ideas, you can contact me directly and we can discuss it together. I'm very open to discuss new ideas. Okay. Okay, I just here in this slide listed the fishes classification, the machine learning application we already, I have already done in the past, and I would like to share it with you. First is fishes classification using well logs. This is actually an easy task and very common nowadays. Porosity production using seismic attributes, the same. But using seismic attributes has some trick parts, but we can do it, of course. And this is already I have done, and I have example here for it. And this is a very, very good solution where classic inversion doesn't work. So in some problems, in some seismic data and some province as well, the classic inversion process is very limited. So here where the machine learning fills the gap, and it's really, really a very good one. Permeability prediction using petrophysical parameters, the same as like porosity prediction as well. Fishes classification using seismic attributes, so we can see the fishes propagating over the field. Since we have seismic, it's not only on the 1D, but now it's on 3D as well. Seismic data inversion using multi-solver problems algorithm. Yes, this is we can do, and I will add another one here. I would discuss with you, of course, which is advanced topic, which is it's called transfer learning. It's part of machine learning, but we can actually improve seismic resolution using machine learning through a new application called transfer learning. I will show you one slide over this one. So I will start with using seismic attributes to predict porosity logs. So we have here the seismic attributes. We have amplitude, first derivative, second derivative, envelope, variance, wave number, because this seismic is in depth, and the phase rotation. And we have here the predicted porosity in red, and we have here the actual porosity in blue, and overlaid the predicted porosity in red. So as you can see here in the background, we have the blue ones, which is the actual porosity, and we have the predicted porosity, which is in red. And as you can see, it's very, very good. It's doing a very good job, the machine learning prediction. This is effective porosity. That's why in some values you see zero porosity, because this is the shale intervals. So this is the effective porosity. And going from one dimension, as we see in before, it's the same cube, same algorithm. It's predicting the 3D porosity cube based on the data labeled from the well logs. So in this area, we have 4 wells. 3 of them as training data, and 1 of them is testing data, and this one is the testing data. As you can see here, we have here high porosity, and we have here low porosity, and see how conformable it is with the seismic. It's not seismic now, it's predicted porosity. So as you can see here, the white reflectors represent low velocity, low porosity data, and the green, yellow colors are presenting the high porosity values. And we come up from the seismic data directly into a porosity without doing a seismic inversion, without doing EVO analysis and this stuff. This is what we call it now, pseudo inversion or machine learning based inversion. Okay. The second one is the phase classification using well logs, and this is very, very common nowadays to do it. This is the well logs we have from one of the wells, and here is the actual lithophases we have, and these 3 columns here are the predicted value by different algorithms. Here we are using support vector classifier. We are using here logistic regression, and here we are using random forest. So as you can see, random forest can pick even the smallest details inside a big body of phase classification. So it's almost near perfection. So we can do a lot of algorithms, and then we choose which one we can do, which will solve our problem elegantly. Okay. This is the one I was talking to you about, which is increasing or enhancing the seismic resolution based on machine learning algorithm. As you can see here, we have here low resolution seismic data. As you can see, low frequencies everywhere, especially here in retrograding delta. And as you can see here from the histogram, from the frequency spectrum, that we already have dominant frequency here is about 17 or 18 hertz. So we have here low frequency data, as you can see, and by using transfer learning and machine learning and transfer learning, we could increase the frequency content from 17 hertz into almost double, 34 hertz, and this has been done in different manner for machine learning. It's not only machine learning; it's another advanced part of the machine learning called transfer learning. And this is what we already use to enhance the signal to seismic ratio. Of course, we got some side effects. As you can see, we have here some dots, and this dots is random noise. We can filter afterwards this prediction, and then we can see better seismic continuity rather than this random noise we have here. But overall, as you can see here, I have here like 4 or 5 reflectors. I have here like 10, 12 reflectors. So I can easily enhance the seismic resolution based on machine learning, and I think this is the most interesting part of machine learning, that we can do things that other techniques, classic techniques, cannot do by its own. This is the same histogram for the previous data. The original data was this high, the red one. The filtered data was here to 17 hertz, and this is the prediction. We could enhance all the way to this from 17 into 34 dominant frequencies, as we mentioned earlier, and this is already gives you the advantage of choosing or doing a machine learning to enhance the seismic quality you have. And finally, final thing, if you don't have any question, I will share this slide, but let's first get some questions. Okay, the first one, yes, you will get the GitHub link, sure. May I have a question? When we forecast production for oil and gas with machine learning time series model, what variable are needed to multivariate time series model? Okay, and this is a very good question. I think it's advanced a little bit, but it's a very good one. In time series model, usually you do have just the production data you have, just the data was associated with the date. So you change the date into days, weeks, months, seasons, and years. And based on this data, you are building your machine learning variables. I would suggest you to work with the profit model, this as first screening, and then you have ARIMA, ANOVA. You have a lot of time series analysis you can do easily in machine learning as well, and you can get a good production over the time series analysis. What is the base to select algorithm type, or depend on what? What do you mean by label data? Okay, great. First of all, your problem will tell you what algorithms you are going to use. Label data, I will answer this first, and then I will come back to answer the first one. Label data, which means when I'm going to predict porosity, I have to have the porosity first. This is the label data. This is the answer. In order to predict it correctly, I need to have the data first, and then if I have the data, so this is the label data. This is the one I'm going to compare the result with, and actually I will go. I will use this data in order to make the algorithm works efficiently to learn, and then I will test against this data as well. So this is the label data. I have to have the seismic attributes I said, and the actual data as well, for example. And the algorithm will learn from the actual data and the input data from the actual porosity and the input data, and try to find the relationship between both of them. And then it will link each other. So at the end of the day, he learned the relationship between the data itself. In such a problem like porosity prediction, you can use, you have to use supervised machine learning. Supervised machine learning, like linear regression, like logistic regression, like random forest decision trees, all sort of algorithms. Okay. If I have limited data, like only 2 wells, I'm still able to do, of course, limited data here, 2 wells, if each well have 5,000 data rows, which means you have 10,000 data points, which is great. You are not treating the data as well by well. You are treating the data point by point. So if I have, as I said, if I have 5,000 rows per well, which means I have 10,000 data points, which is a very good amount to do a machine learning with this data. Sadia Muhammad, thank you. You're welcome. I'm happy that you already I already answered your questions. Okay, the final slide here. The final slide here is the one who for the people who wants to learn machine learning, to be a machine learning educator or machine educators. What is the roadmap? How I can grab the skill set needed to be a machine learning engineer? Actually, it's based on 4 phases. The first phase is you need to learn a programming language. And the most booming programming language right now is Python, R, and of course you will need SQL in order to handle your databases. Python has some libraries. This is the most efficient libraries inside Python, which is NumPy, Matplotlib, Pandas. In R, you have tidyverse, tidymodels, and ggplot. And this is the first phase. The second phase, you need to know how to do data wrangling techniques, how you change data, how you perform different data operations, how to join data frames, what is a data frame, all these definitions and approaches. And you need to learn, if in Python, you need to learn SciPy, ObsPy, or observation by stat models, Plotly. In R, you need to learn tidyverse, tidymodels as well. These are the name of the libraries. You can take this name and just Google it, and you will find a lot of resources that will help you to know how to learn these libraries. The third phase, you need to have mathematics. You need to learn mathematics, statistics, linear algebra, calculus. But I don't want you to be overwhelmed. This is, you don't want to be a PhD student in mathematics. No, you just need the basics, and the basics will be needed or will be learned as you go. So start learning the machine learning techniques, and you build your mathematics knowledge while you are learning machine learning techniques. If you find something you don't understand, then you go and learn what the mathematics behind it. So you don't need to be a PhD in mathematics or a PhD student in mathematics. You just know the basic mathematics. The fourth phase is the machine learning algorithm, and this is can be very easy. I mean, I'm teaching machine learning algorithms all the time. You can follow me on LinkedIn. I'm putting some tips and tricks. I'm explaining what is the machine learning techniques are useful, how it works, what's behind the curtain, how it works, a little bit of mathematics as well. So this is will be easy. So the journey, as we see here, it consists of 4 phases, starting from learning a programming language till you learn already the machine learning algorithm. And you can find here, I put also the geoscience package. It's already Python package. You can search for them and follow in order to equip yourself with everything regarding the geoscience in Python. So in Python, you can have Willy, which is about well data, reading and manipulating. LAS.io, the same. It's already 2 libraries doing the same thing. SigY.io for SigY data, seismic data, reading, writing, and manipulation. PetroPy is petrophysical evaluation, and this can replace clearly can replace any software for petrophysical evaluation. And thank you very much. You can find me on LinkedIn under the name Moslim, and I'm going to share with you my my GitHub. And I'm going to share this slide as well with the company that hosts us today. And I hope see you succeed in machine learning field, because I really see a very good potential in the future for this field. Thank you very much. Glory, yes, this is what we already did. Okay, I can do it right now. Thank you all. Just let me show you my LinkedIn. This is my LinkedIn for people who are interested in following me. This is I'm Muslim from LinkedIn. And for people who are interested to see my GitHub, and I will be happy if you contact me on GitHub. Here is my GitHub already. You will find also under the name of Amr Muslim. Yes, and you will find here another webinars already I have done in the past. For today's lecture, you will find it here under Geoscience webinar, February 2022. Thank you very much. I can put it to you here if you want. And for the presentation, I will send it to the companies that gladly hosts us today, and I can't thank them enough for make this webinar happen. And keep in touch. Thank you very much.
Thank you, sir.
Thank you very much. That was very informative. Shukran.
You're welcome.
Thank you.
You're always welcome. Thank you very much.
Thank you. We appreciate it, sir. Thank you.
Okay. So you're welcome. Thank you very much. Uh,
Sir, follow me on LinkedIn. I will meet you again in the next webinar.